Assalamu alaikum wa rahmatullahi wa barakatuh. We were discussing the linear programming problem. So, in the last class, we have seen how you can have multiple basic solution out of a optimization problem. So today, we're going to see two simple problems, one with equality constant, the other one with inequality constant. So let's begin. The idea that we have developed in the last class that will be utilized here. So this is a maximization problem. Maximization problem. You can say that f of x, which is x1 and x2 and x3 is equal to x1 minus 2x2 plus 4x3, and subjected to the constraints x1 plus 2x2 plus 3x3 equal to 7, 3x1 plus 4x2 plus 6x3 equal to 15. Okay, so we also have to figure out, first of all, we have to find out the basic solution, and then whether we check those are feasible or not. And also, in addition, we'll go for optimal solution, whether the solution is optimal or not. Okay, and also another term is there, whether the solution is degenerate or non-degenerate. So don't worry, while we're solving, we'll discuss the relevant theory. So let's start solving this one. So from this problem, we can see two things. First of all, the number of the variable. Okay, so our n is 3, x1, x2, x3, and number of the constant equation m equal to 2. And this gives us how many variables we have to make 0. So our setting n minus m, that is 3 minus 2 variables to 0. Okay, or we can say that basically n minus 3 minus 2, 1 variable will be non-basic variable. Non-basic variable. Okay, so let's begin. Okay, and also how many solutions we're going to have. So how many solutions we are going to have is basically number of solutions. Number of solutions. NCM. Basically 3C2. So factorial 3 divided by factorial 2, factorial 2, 3 minus 2, that is factorial 1. So ultimately, there will be 3 solutions. So now, let's begin with the table. As we are saying, the tabular form is better. So our for table will be something like this. Number of solution first, number of solution, the first one. Then we'll have non-basic variable, non-basic variable, then basic variable, Then equations and solution. So equations and solution. We can also call this one as a basic solution. So equations and basic solution. Then we'll have feasible solution out of the solution that we have. Feasible solution. And then also you can calculate the magnitude, that is f of x, and also whether it is optimal solution or not. Optimal solution. And last one, degenerate or non-degenerate. So degenerate or non-degenerate. Okay, so we know that you have how many solutions? You have 3 solutions. 1, 2, 3. And then how many variables you have to set to 0? 1 variable at a time. So we'll have 1 non-basic variable or 0 variable, and the other 2 will be basic variable. So we'll start with x1, then next solution, we'll try to set x2 equal to 0, and the third one x3 equal to 0. And then we'll have our basic variables. Those are here x2 and x3, here x1 and x3, and here x1 and x2. Are the equations. From the given equations, the equality constants, we are just going to replace set. In the first case, x equal to 0, in the second solution, x2 equal to 0, and the third, in the first one, x1 equal to 0, the second one, x2 equal to 0, and in the third one, x3 equal to 0. So just find the equation. So 2x2 plus 3, x3 equal to 7, and 4x2 plus 6x3 equal to 15. As you can see, these two are just linearly dependent on each other. So ultimately, it will not give you any solution. So you can say that for this particular case, there is no solution. Okay, so now the second case, x1 plus 3x3 equal to 7, and x3x1 plus 6x3 equal to 15. Now if we solve it, we are going to see that x1 will be 1, x1 is 1, and x2 is x3 basically. x3 is 2. The last case, x1 plus 2x2 equal to 7, x3x1 plus 4x2 equal to 15, and this will give us the solution as x1 equal to 1 and x2 equal to 3. Okay, so three solution we figured out. In the first case, actually, there is no solution. Now, whether our solution is feasible or not, we have defined the feasibility by saying that whether the values, the non-basic variable values are 0 or not. So in the first case, there is no solution, so no question about that. But in the second case, we can see that both of them, x1 and x3 are positive, so solution is actually feasible. And in the third case as well, x1 and x2 both are positive. So the solution is basically visible, yes. Now, function value we can calculate with the value x1 equal to 1 and x2 equal to 2 from the given equation. If we plug in, then we're going to see that we are going to get a magnitude of 9. Similarly, we're going to get a magnitude of -5. So out of the 3 or 4 solution, in general, one of them will be optimal. And in this particular problem, basically, it is a maximization problem. So we can easily see that this value is our maximum for this particular problem. So only in this case, we can say, yes, this is the optimum solution. And non-degenerate or non-degenerate, this is actually related to the fact that already our non-basic variable is 0. So out of the other two, that is basic variable x2 and x3, whether any one of these are 0 or not. If these are non-zero, then it is non-degenerate. Okay, so since, as you can see, the first one doesn't have a solution, so we are not going to go for any one of those. But here, this is non-zero, this is non-zero, this is non-zero. So that means these are non-degenerate. Okay, so non-degenerate. Similarly, here as well, non-degenerate. Okay, so we figured out basic solutions. Out of that, we also figure out whether those are feasible or not, basically non-zero or not. And then we figure out whether those are optimal or not. So this is the example problem 1 with equality constant. Now let's see the problem 2 with inequality constant. So problem 2. So first of all, the function fx given as 2x1 minus 2x2 plus 4x3 minus 5x4. This is also a maximization problem, so maximize the function and subject it to x1 plus 4x2 minus 2x3 plus 8x4 smaller than or equal to 4 minus x1 plus 2x2 plus 3x3 plus 4x4 smaller than or equal to 1. And also, this is in general given xi greater or equal to 0, where I ranges from 1, actually 1, 2, 3, 4. So this is now the first thing first, what we should look for is basically what is n, our n equal to 2, number of the variables, and m equal to number of the constant equation. So how many, n is 4. How many variables we have to set to 0? So variables, or basically you can also call them non-basic variables, is basically n minus m, that is 4 minus 2. Basically 2 at a time you have to set equal to 0. And also number of the solutions. So number of solutions that we will have is basically NCM. So 4C2. So factorial 4 by factorial 2 factorial 4 minus 2. Ultimately, it will give us 6 solutions. So basically 6 trials you have to give. Okay, so now let's go for the table. So in the similar table, we have to find out. So first one will be number of solutions. So number of solution. So first column. So I'm trying to write a bit short with short notice in this time because we already have explained the thing. So non-basic variable, basic variable, and then we have equations and solution, basic solution, basic solution. And then we have feasible solution. So feasible solution. Then we have optimal solution, the magnitude of the f, x. Then optimum solution, optimal solution. Then degenerate or non-degenerate. Okay, so since we have limitation in the space, so we are trying to make things in a smaller space. Okay, so let's try with basically should take a bit more space for the equations and magnitudes. Optimum or not, that's and degenerate or not. So we should have 6 of them. So 1, 2, 3. Then we should go with 4. Okay, let's solve 3 first, and then go to the next 3. So just saying that x1, x2 is non-basic. So x1 equal to 0, x2 equal to 0. Then basic variable will be basically x3 and x4. Okay. So this is case number 1. Case number 2, basically all possible combinations that we have, you have to take those. So next one is x1, x3. X3, so x2 and x4 will be our basic variable. Then we'll have x1, x4, x1, x4. So here will be x2 and x3 will be our basic variable. Then case 4. Case 4. Five and 6. Okay, so then it will be x2 and x3. x2 equal to 0, x3 equal to 0. Then x2, x4, and finally x3 and x4. Okay, so similarly x1, x4 here, x4, x1, x3, x1, x2. So Okay, so just eliminate x1 and x2, write the equation, then we're going to get minus 2x3 plus 8x4 equal to 2, minus 3x3 plus 4x4 equal to 1. So this will give us x 3 equal to 0 if we solve it using the calculator, and x4 equal to 1 by 4. Next, 130. So you can write 4x2 minus 2x3 equal to 2, 2x2 4x2 plus 8 plus 8x4 equal to 2, and then you will have 2x2 plus 4x4 equal to 1. So since, as you can see, the variables are actually linearly dependent, so there will be no solution. No solution. Third case, 4x2 minus 2x3 equal to 2. Then 2x2 plus 3x3 equal to 1. So x 2 will be 1 by 4, and x3 will be 0. Okay, so fourth case, that is why we wanted to keep a bit space, but somehow, okay, fourth case, x1 plus 8x4. So x1 plus 8x4 equal to 2, minus x1 plus 4x4 equal to 1. So ultimately it will give us x1 equal to 0 and x4 equal to 1 by 4. Fifth case, x1 minus 2x3 equal to 2, minus x1 plus 3x3 equal to 1. So solution will be x1 equal to 8 and x3 equal to 3. Last case, basically x1 plus 4x2 equal to 2, and minus x1 plus 2x2 equal to 1. The solution will be x1 equal to 0 and x2 equal to half. Okay. So now let's fill up the rest of this table and try to find the solution. Now, feasible or not? Definitely feasible, because of the fact that there is no, we don't have any negative values. Okay, so feasibility is actually linked with the negative values, not zero. In the previous problem, we say that it has to be non-zero. Actually, not non-zero. It has to be non-negative. Okay, so look at the last table. So both of them, none of them is non-negative here and here. So that is why they are actually feasible. So feasibility goes with the non-negativity. Now, the first case, is it feasible? Even though we have a 0, yes, it is a feasible case. And the second one, there is no solution, so we will not do anything about that one. The third one also, there is no negative, so all of them are feasible. This one is also feasible. And this one is, both of them are greater than 0, so all of them are actually feasible solution. And what about the value? If we calculate the value, we are going to get that this is minus 5/4. Then this is minus half. This is minus 5/4. Then we have 28 and minus 1. So from the magnitude of the phi f of x, we can easily can identify that this is our optimum value or maximum value in this case. So we can easily write this is our optimum scenario. And now whether degenerate or not. So for the degenerate case, we have to check whether we have additional zeros in the basic variable. So basically, you can see that in the first case, this is 0. So this is basically degenerate. There is no solution. Here we have 0. So this is also degenerate. And this is 0 as well. So degenerate. This is both of them non-zero. So this is actually non-degenerate. And last one is also degenerate. Okay, so this is how you have to solve the linear programming problem and to figure out optimal condition. And what is the significance of the degenerate or non-degenerate while we are solving the simplex problem with the simplex method? Then we're going to see that whenever there is a degenerative case, there is a possibility of having alternative solutions. Okay, so this is the end of your the 2 additional problems of the linear programming problems topics relate to that one. So see you in the next class, inshallah. Assalamu alaikum. Bye.